Okay, let's continue what's the last material that we have so far. Last time we talked about functions being even or odd. Okay, even or odd is just symmetric, but there are more functions with no symmetry at all. So it is not a choice between either even or odd, but functions can be not even, not odd, neither odd nor even, or you have all kind of possibilities there. Okay. So, and the multiplication table for even odd functions looks like this one. So it's quite different from a multiplication or of numbers, odd even numbers. Okay. We'll see that later because you see odd, even and odd functions are properties of symmetry with respect to reflection of x-axis or both x-axis and y-axis. Okay. All right, so that's it last time. So we'll start with this. Okay. Let's start with the function that we call a rounding functions. Up or down. Okay. So if we start with the real number, then this is the notations. Okay. So this is round down of x. So you round it to round it down. So for example, if you round this number 5 is still 5, but if you round 5.1, you say it's still 5 also, even 5.99, so it's still 5. Okay, and what about negative? Well, so 0 first. You round 0, still 0. Negative 1.2, for example. Well, if you round this number, it becomes negative 2. Okay, because you round to the nearest integer less than that number, less or equal. Okay. Are just integer less or equal to x. Okay, so that's the what we call round down. And sometimes we call it floor functions. Okay, and as a counterpart, we also have some book use this one, but we use in Purcell, we use these notations, sort of what you call it, square bracket, but with this double bracket. Right? So this is what we call, this is the floor functions. So this round down floor functions. And we have also what we call a round up. This is called ceiling function. Okay. So you see, this is if you're standing. If you're standing, then your feet would be on the floor. Not to say that your head would be up to the ceiling, but somehow that's the idea. Okay. And you see they have um, some relation. For example, uh, you have x. If you run it down, yeah. If you round up, you have ceiling. Okay. See that the relation is that uh, round up is just a round down at one. Okay, is it clear enough?
Yes, sir.
Okay, so let's see how the graph looks like. Okay, all right. There are two ways to see these functions. For example, if you check this one out one by one, well, it's very much depend on the values. Say if x is between 0 and 1, so x between 1 and 2, x between 2 and 3 and up, -1. So it's kind of long. Let's the value here is 2, value 1, 0, -1, -2, and etc. Here going down is going up, right? So uh, if we try to graph this, this would look like, let's see, this is 1, 2, 3, 4, 1, -2, -3. Okay, here. Okay. All right. So if we, so between 1 and 0 and 1, for example, here the value is 0. So right, 0 is included, 1 excluded. Oh, excuse me. Sorry. Okay, so between 1 and 2, the value is 1. So 1 included, 2 excluded. So and here we have similarly, here we have right? Here, sorry, should be here. Okay. Oh, sorry. Here we have right? So you see, that's how we call this a step functions. Okay, because it looks like stair function, uh, staircase, or okay. So that's how you get the. What about the ceiling functions? Well, you just because we have these relations, the ceiling functions is just the floor functions. Add one. Add one here means you translate this up by one. Okay, so this is floor functions. The ceiling functions, since is the floor functions at one. So this is just of ceiling functions is the graph of floor functions. You translate one up. Okay. All right. Let's see. There is an easier way how to get this function. The graph of floor functions. Okay, how to do this one? Okay, so start from here. Start with y equal x. Right, so this is the diagonal. Okay, and how to okay, so let's do this one. One, two, three, four. 1 minus 2 minus 3. Okay. 1, 2, 3. 1, negative 2, negative 3. All right. So this is the diagonal. Right. This is y, x. Okay. So let's see. Uh, what I would like to do here is let's sorry. Yeah. All right. Here. Let's see. Let me just probably would be easier with this. Okay. All right. So here we have so this is floor functions. Sorry, the diagonal, so y equal x. Okay, and let's see. Okay, we suppose this is 1, 2, 3, 4. Okay, all right. So you see, this is the value of here's the value all x which has values 1 more between uh, 0 and 1. So over here we round it down to this one. Okay, here's the value is between 1 and 2, you see here. Okay. So we round it down to 1. Okay. Here's the value is here between 2 and 3. So we round it down to 2. Same thing here, round it down. Here we get oh sorry, this is supposed to here. Okay, so now it's easy if we uh, so what we see observe the value uh, round it down. Okay, so for example, we apply this to something more slightly more complicated. Let's see, graph y equals square root of sorry the square of x. So we start with the x squared, so the parabola. All right, so let's draw it. Suppose this is, let's see, 1 or the 4. Okay. Okay. Uh, let's see. I would like to make it something bigger. So our 1 here, 2, 3, -1, -4. Okay. Here's the, so it's not as of the same scale. All right. So here's the 4. What's wrong? Something wrong. Let it. Oh, okay. Okay. This is 1, 1, 2, 4. Okay. So this looks like the same thing here. Okay. Not that good. This part should be there. Go. Um, okay, so let's look at the uh, values here. All right, so here's the value uh, between 0 and 1. Okay, so where's that happen? This happens here, right? Between 0 and 1. So round it down to 0. Okay, so this 1 not included, but here everything 0. Okay, now between 1 and 2, everything is rounded down to 1. Where does it happen? It happens here. So we have here, right? So up to here. Same thing here. 2. Okay. Between 2 and 3 here. Between same thing here. So this is between 2 and 3. Round it down. Get this one. Between 3 and 4, round it down. Get between here, round it down. Here, round it down. Okay, same thing here. Similar. Round it down. Here, round it down. Round it down. Okay, so that's how you get um, the graph of the graph of this functions x squared of rounding, sorry, floor function of x squared. Okay, in fact, you can do with uh, with any graph. Graph of find graph of okay. So for example, this one. All right, that's okay. So let's see. Okay, so let's see everything's between 0 and 1, right? Between 0 and 1. See here, between 0 and 1. So here's you round to here. This is the value. So you round also here. Okay. Where's that happen? Here. Okay, and then between 1 and 2. Here's between 1 and 2. So, okay, between 1 and 2. Here's here. Another, this one. And another is this one. And oh, still this is going there. Okay, between 2 and 3, right? So only this one. Here's, yeah, this part. Between 3 and 4, this part. Okay, let's see. Between, there's down the, on the negative y. Here's we have, oh, okay, so here's we have, okay, here we have this one. Okay, so the red one is the floor function of f. Okay, in this case you will see more clearly this is like a staircase function. Going up and down. Okay. Questions?
I have a question.
Sure.
So the one that has the full circle
Mhm.
is the one on the line? Where's the one with the hollow circle is?
Just check the case, okay? Whether it's the endpoint, always check the case, the endpoints. Okay. So for example, this one. All right. What are the value here? Is this included? Where's this value is round down here, right? And let's see here. The value is 2 in this point, at this point, 2. So when you round it down, where does it go? To 2, not 1. So this goes to here. Okay. So just slightly, just be more careful at the endpoints, whether you should put like this or the solid dots or the hollow dot or hollow dot. Okay, just check one by one. Sometimes uh, sometimes you don't need this very careful though. This sometimes. So it's not always the case that the solid one into the left and the hollow one to the right. Depend on the function whether it's going up or going down. Monotone decreasing or monotone increasing. Okay, you just check the value. Okay. More questions? Okay, we'll combine this later on. All right. So let's go to some trigonometry. All right, so we have two versions of trigonometry, trig functions. One is this is what we call a triangular trigonometry, and one is a trig calculus. Okay, so this is a all right. If we have a circle, unit circle, Okay, and we draw a triangle inside this the circle. So this is one. Sorry, one, one, four. So we draw a circle. Right. Suppose this is the point X, Y, coordinate. Right. Okay, so let's see. This is called the R hypotenuse. Uh, draw a right circle. How do you call it? Right circle or perpendicular? Yeah, right triangle with a one vertex is just 0, and at the unit circle. Okay, so this is, let's say this is xy. So the hypotenuse is, right, by Pythagorean theorem. Okay, so we call these functions defined trig functions. Not trig functions, trig, I would say just quantities, trig ratios. So, okay, so what we call a cosine. Oh, this the angle is alpha here. Okay, so cosine alpha ratios creating angle and x y. Okay, so cosine alpha is x over r, so hypotenuse, and sine alpha is, okay, and 3, what you call tangent, is sine over cosine. All right, so the elementary things, the most basic things is cosine and sine. Tangent is the ratio of sine cosine. So all these ratios between the base and the height of the base, height, and hypotenuse of a right triangle. Okay. Okay, so this is a what we call a triangular trigonometry, because we start from from a circle. So of course it has values here. All right, for example, here, okay, so this first quadrant, because x is positive, x and y is positive both, so you have a here, if the cosine alpha is positive, let's see, sine is also positive. Why? Because see, x is positive, r is always positive. Okay, here you have x is negative, sine is y is positive. So you see here you have cosine is negative, but your sine is still positive, right? Just because the sine Here you have x and y both. X and y is negative, right? So sorry, where's what I'm sharing? Okay. Um, cosine. Here you have sines negative and cosine also negative. Here you have, let's see, x is positive, so cosine is positive, sine would be negative. Okay, because of this, the value here. So in the first quadrant, second quadrant, third quadrant, and fourth quadrant. Okay, and based on based on what you know, what do we know about triangle? So use a lot of Pythagorean theorem. We can compute sine and cosine. Right? So, for example, here we have cosine 45 degrees, means that you have, this is 45. So if this is 1, this should be, let's see, x and y should be the same, right? And you have x squared plus y squared equals 1. That's so x squared is 1/2. So you see squared. Okay, so this is what the 1/2 square root of 2. Okay, so in this case would be cosine 45 degrees equals sine 45 degrees equals. Okay. All right. So in special case, what about 90 degrees? There is no triangle here. Okay, so, but in this case, you see that the x would be y equals 1. Oh, sorry. Y equals 1. X equals 0. Okay, so in this case would be cosine, what, 90 degrees is 0. Sine 90 degrees is 1. Okay, so you can start computing sine and cosine of numbers. So in this case, our trig would be angles, changing angles into ratio. Okay, so you feed angles and you get a ratio. All right, and you have all kind of um, triangular trig identities. Okay, um, the one that we use quite a lot is that this one. This is 1. We call this Pythagorean identity. And you have double angle formula. step. Anyone recall this identity?
It's 2 times cosine times sine.
This is sine alpha cosine alpha. Cosine. Oh, this is just something more general. Okay, so this is sine alpha cosine beta, and let's switch sine and cosine. Sorry. Sine alpha, sine beta. Okay, and what about cosine? Well, this is cosine alpha cosine beta minus sine alpha sine. And if you have subtraction, so we have this. Okay, and from here you get double angle identity. Sine 2 alpha, cosine 2 alpha. I won't write this down. So this is the some of the basic identities in trigonometry. Okay, so here's alpha is between 0 and 180 degrees. Sorry. Yeah, 60 degrees. Okay. All right. So trig is basically changing angles to ratio. Okay. So from how's the graph looks like? Well, the thing here is that how's the graph looks like? So let's see. So if we draw this, say this is 360. This is okay. For example, what about sine alpha? Okay. Here you, all right, so we know this the 180, this is 90. Okay, so the graph looks like this one. Sorry. Not good. Okay. Here's the same thing. Okay. But the thing here is that 360 degrees is equal to degrees. Let's see, 360 over there. Okay. So multiple of 360 degrees. So these two numbers, sorry, this and this, they should be the same. Well, if you if you draw this on a piece of paper, well, what we do is actually you not really fold, but round the paper so that what you have is this is the x-axis, right? And so here, 0 degrees, all coincide. Okay, so when we draw this diagram here, that's the 180 degrees. Okay, so how the graph looks like? Well, the graph looks like, let's see, let's draw this one. This is one, for example. All right, so this is, the value is 1. Here's value should be -1. Okay, so the graph looks like this one. Okay, can you imagine the picture? Can you picture this, the graph on a cylinder, right? So the graph is actually drawn on a cylinder. Okay, it's cylinder because of this. Due to the fact that there. Okay, you can draw this in a picture and then just fold it. Questions? All right, but something that we cannot do with this triangular trig. With the triangular trig. For example, is, well, let's compute this composition, sine, cosine of sine alpha. Well, this is not defined. Right? Why? Because alpha is an angle, and with trig, sine become a ratio, right? But it's not compatible with the cosine because there's no way you can apply cosine to ratio. To ratio. So that's the reason why this compositions is not defined. And composition is important in calculus. So we can't do this triangular trace for calculus. Right? So composition is of trig functions are undefined. Okay. And one more thing here is that in calculus, we would like to compute this quantity given. You compute this one. I guess so it's alpha plus h minus. Okay, so this difference and divide by h. Okay, so let's see what if f is a trig functions. So angle becomes ratio. Okay, so let's see here. This is angle. So h should be angle to be able to add to alpha. This is angle, right? This angle. So you apply f trig functions. So the whole thing here is the ratio. It's a number. Okay, so you subtract those numbers, you get a number. But there's common an odd thing here. This angle. So what you have here is that you have a number divided by angle. What kind of creature is number divided by angle? Okay. So, for example, if you have 5 degrees divided by 2, for example, you can say this is 2.5 degrees. Okay. But the thing is, what about 5 divided by 2 degrees? What kind of animal is that? Okay. So it doesn't say this is angle the other way around. No. Right. So this is undefined. So division by angle is undefined. So we cannot compute such a thing. Okay. Oh, by the way, has anyone noticed where are we going to find this kind of quantities here? If anyone ever noticed this one, observe this one, whether it appears in anything that you know about the calculus when you learn calculus in high school.
Is that differentiation?
Yes, exactly. Later when you find derivative, we need you to compute such a thing. Okay. So that is one of the basic things in calculus. So with trig functions like this, it's unclear how we should compute later on calculus. Okay, so we need to so for calculus, modify trig. So 1 and 2, sorry, this is 1 and this is 2 are defined. Okay, so we will modify the trig, the triangular trig. Okay, and we call it a calculus trig. All right. Okay, let's take a break for 5 minutes and we'll start again. Let's stop here.